Hi students, thank you to everyone who's submitted work for 6A already. It's really useful for me to see where you guys are having difficulty, and especially a big thank you to Lucy, whose really thorough answers to the survey helped me understand that you guys are definitely a bit further back in methods than I anticipated, and have not covered some of the calculus that I clearly took for granted in the first video. I've had a bit of a think and I've looked at all options, and I think the best thing for us to do is still continue as we are with the current plan, but I want you to be really confident and sure about what that means. So here's our plan that you've seen before, and obviously we have delayed the SAC because we don't know exactly when that's going to fit in, and that means that a lot of the calculus has been brought forward ever so slightly. That does mean you'll be doing it in parallel with methods, and it means at times we'll be doing something in specialist just before it's come up with in methods. I had to think about changing things around and bringing forward some of the mechanics or some of the stats, but I don't think that's a good idea at the moment. The mechanics requires calculus, so that wouldn't really help us at all, and you're going to be doing some stats in methods that is a precursor as well to what we're going to do in specialist, and so bringing that forward doesn't really help us. So this term is a big term for calculus. You're going to be doing it all in methods, you're going to be doing it all in specialist, and what I just wanted to say is that makes it, I think, a really big make or break term for you guys. If you can stay up to speed and master things as we go along, then you'll be in an incredible position going into term 3. You just don't want to be the person who isn't quite getting it to grips with the remote learning, falling behind a little bit and not asking for help. And so I want to just introduce a couple of ideas to you for how to do that. The first is that if at any point you are feeling like you are a little bit at sea with the calculus, then you can go and do some extra practice on more straightforward questions. So for example, with the 6A work that I just set you, obviously the contract questions begin at number 5 here, to move us on to the more challenging things. But you might have decided, and you might decide, that practicing question 1, 2 and 3 is going to be really important for you to master that chain rule, quotient rule and product rule before going on to the more difficult things. And I really encourage you to put in that little bit of extra work and to build your confidence as you go through. The other thing, of course, is that you can refer to the methods textbook and find questions and basic explanations for some of the underlying concepts that we're going to be doing in specialist. So in the methods textbook here, I can find a whole section on the chain rule and a proof for it, examples and questions. And I want you guys to move confidently backwards and forwards between the two to fill in any gaps that you have if something isn't quite clicking. So please take control of that situation, do that extra little bit of work where it's going to be the thing that helps you personally, and let me know when you're doing that if it's slowing you down a little bit. The second thing is I will try and do some of these review videos as we go through. I don't know if I'll be able to do one after every single lesson, but if you flag up to me, either by email or just when I review your work, questions which you found challenging, then I'll post a video just going through a couple of them to help you master it a little bit quicker. So from 6A here, we'll jump straight in. I've chosen 3 questions based on people's work, and I'm going to show people's work here that I wanted to talk about in addition to the first videos about the notes. So for question 5, I want us just to look at what we do when we have the chain rule inside another rule. For question 8, I wanted to look at those log of a function questions, and in particular just ways to simplify them. And then the last thing I wanted to do is just talk, I'm not going to solve question 11, but just talk about the idea of stationary points. So first up, question 5, and big thank you to this student who had identified a couple of questions in their work that we can focus on here. So the first question I see is, why do we need cos x here? Where does that come from? And I'm going to touch upon that. And the other one is, why is the g of x function for part E sine of x squared and not just x squared? So I'm going to go on to this now, and hopefully by focusing on 5d and E answer those questions. So give me a second. So question 5d, y is log e of x times e to the power sine x. Just like this. And the first thing to think about as we're doing this is, what rules are we going to use? And we can see a product of two functions. So I'm definitely going to use the product rule. And then what we're going to talk about is that we have, in addition, a chain rule within that product. So first of all, for this question, if I write out what my my group of 4 and smaller functions are going to be, I've got the first function u, which is log e of x, and I've got the second function v, which is e to the power sine x. Du by dx is easy, that's one of our standard results, that's 1 over x. But dv by dx is a little bit more challenging because we're trying to use our chain rule within like this part of the question. So I just wanted to talk about that as like the chain rule within another question. So we have this form of the chain rule, which is to say that if we differentiate g of h of x, what we do is we take the inside function, we differentiate that, and then we multiply it by the derivative of the outside function, but still containing the inside function. And this idea, if we can develop this pattern, memorize it, helps us with simple versions of the chain rule like this, where we don't even have to write anything down. So this process, we've got an inside function h and an outside function g. We differentiate the inside function and we multiply it by the derivative of the outside function. So in this case, the inside function is sine x and the outside function is the exponential. So what do? We differentiate the inside function, giving me cos, and we multiply it by the derivative of the outside function. The outside function is an exponential, so nothing changes. So, using the chain rule in our heads, dv by dx would be cos x multiplied by e to the power sine x. It's that process that if we can get really fluent, if you can get really fluent, will help you answer these questions with confidence. So in this case, dy by dx is u dv by dx plus v du by dx. That's just the chain rule. So it's going to be log e of x times cos x e to the power sine x plus e to the power sine x times 1 over x. And then if we just factorize, that's e to the power sine x times log e of x cos x plus 1 over x, which is the answer in the back of the book. Looking at Q5e, that question is to differentiate y equals sine cubed of x squared, and the question that the student asked on their work was, how do you decide what is the inside and the outside function here? We remember that sine cubed, what that really means is sine of x squared all cubed. And so the outside function, if we're going to break this apart, really has to be u cubed, the cubing. And then what you could do this formally by saying, well, actually this is three functions inside each other. You have x squared inside sine, and you have that inside u cubed, cube function. But using this idea of the simple chain rule in our heads, we don't actually have to go to that extra layer. Instead, what I'm going to do is I'm going to say, well, look, y is equal to u cubed, where u is sine of x squared. dy by du, that's straightforward, that's just 3u squared. And du by dx, well, I'm going to do the chain rule in my head. I'm going to think my inside function is x squared, my outside function is sine. So I differentiate the inside function, giving me 2x, and then I multiply that by the derivative of the outside function. Derivative of the outside function is cos. So again, another step that if you can be confident and you can do these type of chain rule questions in your head, we don't need any additional working out on our page, because now we can just say that dy by dx, using the chain rule, is the same as dy by du times du by dx. So it's 3 times u squared, and u is sine of x squared, times 2x times cos of x squared, which overall gives me 6x sine squared of x squared cos of x squared. That also is the answer in the back of the book. So just to take it back to the question that the student answered here, hopefully that's cleared it up. Please obviously ask me if that's not the case, but the cos x for the first question comes from the derivative of the inside function where we do that chain rule, and here we for part E we are defining the inside and the outside functions. The outside function here has to be y equals u cubed. Okay. Alright, moving on to question 8, and quite a few students I saw had some issues with this, and what I'm going to focus on is E and H. So there's a couple of things here. The first thing to say is there's like a method for doing the log of a function, and once we've kind of got that down, that can help us out massively. The other thing is to do with simplifying our answers, and some tricks for doing that. So first up, if we look at 8e, for 8e, y is natural log base e of the modulus of cosec x plus tan x. And because we have a function of another function, we're definitely going to be using the chain rule here. So we're going to have y equals log of u, where u is, log of mod u, to be formal about it, where u equals cosec x plus tan x. Dy by du is 1 over u, and the first tricky part of this is to evaluate du by dx. Now, tan x, hopefully we are all on message that bit is relatively easy. Tan x differentiates to sec squared x, it's a known result, but we haven't talked about known results for differentiate cosec x. I was really encouraged to see in the work lots of students who'd figured that out for themselves, but I'm just going to pause and go through that a little bit, and hopefully that would help you with other reciprocal functions like sec and cot. So if u equals cosec of x, one way of writing that is that it's sine of x to the power minus 1. And then what I'm going to try and do again is this idea of the chain rule in my head. So, du by dx, I've got an inside function which is sine x, and I've got an outside function which is something to the power of minus 1. So, first thing I'm going to do is I'm going to differentiate the inside function. Inside function differentiated gives me cos x, and then I'm going to multiply that by the derivative of the outside function, which is u to the power minus 1. Obviously what I do there is I multiply by the power, so multiply by minus 1, and then reduce the power by 1. So differentiate the inside function, then multiply it by the derivative of the outside function, still with the sine x within it. Simplifying this a little bit, we have minus cos x over sine squared x, and in some cases we're going to leave it like this because taking things back to cos and sine is often a good way to help us simplify our functions. But those of you who have looked up the known results for this, or the way that we often write it, we can simplify it by saying that's minus cos x over sine x times 1 over sine x. So that's the same thing as cos over sine, which is cot, and 1 over sine, which is cosec. So the derivative of cosec x is minus cot x cosec x. Sorry, that's quite small there. Minus cot cosec. So we feed this in to our chain rule to try and solve. So dy by dx is the same as dy by du times by du by dx. So that's the same as 1 over cosec x plus tan x times by minus cot x cosec x plus sec squared x, which, if I were to write it as one fraction, is the same as sec squared x minus cot x cosec x all over cosec x plus tan x. So, as one fraction. Now, this, sorry, losing you here a little bit. Not ideal, must do better. Okay, this here is technically correct. This is a final answer, and you do have to be careful with these type of questions a little bit from assuming you're wrong just because your answer doesn't match what's in the back of the book. So if you successfully got this, well then you're 90% of the way there. This is a correct solution, but as we know, in questions we might be asked to write something in a particular form, and if we have these kind of less common circular functions as part of our answer, one option is that we can always take everything back to sine and cos to simplify, and that's what they did to get the answer in the back of the book this time. So let me just show you through that. Take every function and write it in terms of cos and sine. like so. And then what we're going to do is we're going to eliminate all these fractions within fractions. We don't like those. So I'm going to try and find the biggest denominator that I need to multiply, or sorry, the smallest denominator I need to multiply everything by to eliminate the fractions and fractions. So if I multiply by cos squared, for example, this is no longer a fraction. This is no longer a fraction. But I need to do something about the signs. So if I multiply by cos squared sine squared, these terms are no longer going to be fractions. These terms are no longer going to be fractions. And that's what I'm going to do. So I'm going to multiply everything by sine squared cos squared on the numerator and the denominator, which is going to give me the following terms. So multiply by sine squared cos squared is going to give me sine squared x minus cos cubed x all over sine x cos squared x plus sine cubed x cos x. This is much more close to what's in the back of the book, and in fact just a little bit of factorisation on the denominator and you're there. So remember this trick of turning everything into sine and cos to simplify, because a couple of people, that's where they came undone. The other specific question I wanted to look at, just based on some people's attempts, was h here. And h was y equals log of x plus root x squared minus 4. And it's another one where the trick is really just in the simplification. So it's chain rule. We write out our block of 4, log of mod u, and u being x plus square root of x squared minus 4, and then we differentiate both of those. dy by du is 1 over u, we're really getting used to that one now, whereas du by dx is 1, and then we're going to do the chain rule in our heads again. So if it helps you, this is the same thing as x squared minus 4 to the power a half, showing us really clearly that the inside function is x squared minus 4, and the outside function is to the power of a half. So what do? We differentiate the inside function to give me 2x, and then we multiply it by the derivative of the outside function. So multiply by the power and subtract 1 from the power for any polynomial. And simplifying this a little bit, 2x cancels with the half, just giving me x, and to the power minus a half means 1 over x squared minus 4 to the power a half. So this is our expression for du by dx. If I then go back in and apply the chain rule for the overall question, I get dy by dx is dy by du multiplied by du by dx. So these two values from the right hand side, meaning I've got 1 over u, which is 1 over x plus root x squared minus 4, and I've got 1 plus x over root x squared minus 4. Now at this point, maybe it's a little bit challenging to see how we can simplify these, but this second term I'm going to try and write as one fraction, because actually I can see that what's going to happen if I do that is it's going to come out as root x squared minus 4 plus x over root x squared minus 4, and now I have the same expression as the denominator for the first term. So those cancel, leaving me with a very straightforward answer of 1 over root x squared minus 4. So there's something about simplifying expressions like this to write them as one fraction and then to look for some cancelling. Okay, slipping off the screen again, my apologies. Okay, those are the questions I wanted to go through in detail, and then the one other thing I just wanted to say, based on some people's questions is that for a number 11 here, where it talks about stationary points, you're going to do a lot more on this in methods, but stationary points occur when the gradient is equal to 0. So to start off question 11, what you're going to do is you're going to differentiate the right-hand sides of f of x there, which should be okay to do. And then you're going to set that equation, or that expression for f dash of x equal to 0. You're going to solve that. It then says about the nature of stationary points, and I think you probably have done this before, but if a stationary point occurs when f dash of x equals 0, we can then analyse the nature of it. A stationary point is a maximum if the second derivative is less than 0, and it is a minimum if the second derivative is greater than 0. So for this question, to fully answer it, what you need to do is you need to differentiate once and equate it to 0 and solve, and then to answer the second part, we need to differentiate the same function again. And I'll leave you guys to do that if you haven't done it already. I hope this is helpful. Please continue to send me any questions you've got along the way. I'm really confident that we can make the most of this period of remote learning and learn as effectively, if not more effectively, as we have been doing in school. So, good work so far, stay disciplined, and yeah, get in touch if you need anything. All the best.